Genesis of chemistry, a complete solution for research and development.
Do you know the difference between mass and weight? It might seem like a simple question, but the truth is, these two terms are often misunderstood and used interchangeably. That's because the difference between them is subtle, yet so fundamental, especially in the realm of physical sciences and engineering. So let's dive right into it. First off, let's talk about mass. Picture this. You're holding a baseball. When you think about the mass of that baseball, you're considering the amount of substance or matter that makes up the ball. It's an intrinsic property of the object, meaning it's inherent to the baseball itself. Whether you're holding that baseball here on Earth, or on the moon, or even if you somehow manage to throw it into deep space, its mass would remain the same. That's right. The mass of an object doesn't change irrespective of its location or the external forces acting upon it. Now, isn't that something? And when we measure mass, we use kilograms. This is a scalar quantity, which means it only has magnitude, not direction. So, the mass of a thing tells us about the quantity of matter in it, and it plays a role in other physical properties too. It influences inertia, the resistance of an object to any change in its velocity, and gravitational pull, the force that attracts two bodies towards each other. So, in a nutshell, mass is the amount of matter in an object, and it stays the same no matter where the object is. It's like your personality. It's a part of you no matter where you go or what you do. But remember, mass is just one side of the story. In our next scene, we'll delve into the other side of the equation, weight. And as we'll see, while mass is constant, weight is a little more, shall we say, variable. But more on that later. Stay tuned. Now that we understand mass, what about weight then? Well, weight is a whole different ballgame. While mass is about the quantity of matter in an object, weight represents the gravitational force acting on that object. Imagine you're holding an apple. The mass of the apple is the amount of stuff that makes up the apple, but its weight is the force with which it's pulled towards the center of the earth. That's gravity doing its thing. You feel this force as the weight of the apple in your hand. Unlike mass, weight isn't a constant value. It changes depending on where you are in the universe. This is because weight depends on gravitational acceleration. Remember that apple in your hand? If you were to take it to the moon, it would weigh less than it does here on Earth. That's because the moon's gravitational acceleration is much less than the Earth's. But if you were to take that same apple to a planet with a stronger gravitational pull, like Jupiter, it would weigh more. The mass of the apple hasn't changed. What's changed is the gravitational force acting on it. And here's another twist. Weight is a vector quantity, meaning it has both magnitude and direction. It's not just about how much force is acting on an object, but also in what direction that force is acting. In the case of weight, that direction is always towards the center of the gravitational source, like the Earth or the Moon. Now, how do we measure weight? You might be thinking in pounds or kilograms, but technically, those are measures of mass. In the world of physics, weight is measured in a unit called the Newton, named after Sir Isaac Newton, the guy who cracked the code of gravity. 1 Newton is the force required to accelerate 1 kilogram of mass at the rate of 1 meter per second squared. So unlike mass, weight changes based on where in the universe the object is. It's all about the gravitational pull. It's clear that mass and weight are different, but how are they related? This is a question that often arises when we delve into the world of physics. To unravel this relationship, we need to bring in a crucial player: gravity. The relationship between mass and weight can be understood through a simple formula: weight equals mass times gravitational acceleration. Let's break this equation down. The term mass refers to the intrinsic property of an object, the amount of substance it contains. On the other hand, weight represents the force exerted on an object due to gravity. The gravitational acceleration is the rate at which an object accelerates towards the Earth due to the force of gravity. Now here's where it gets interesting. The gravitational acceleration is not the same everywhere. In fact, it varies depending on where you are in the universe. For example, on Earth, the gravitational acceleration is approximately 9.8 meters per second squared. However, if you were to stand on the Moon, the gravitational acceleration would be about 1/6 of that on Earth. This variation in gravitational acceleration is why your weight can change depending on where you are. If you were to travel from Earth to the Moon, your mass, the amount of substance in your body would remain the same. However, because the moon's gravitational acceleration is smaller, the force pulling you towards the moon's center, your weight, would be less. This brings us back to our original equation. Weight equals mass times gravitational acceleration. Given a constant gravitational field, an object's weight is directly proportional to its mass. This means that as the mass of an object increases, so does its weight. Conversely, if the mass decreases, the weight decreases as well. Therefore, an object's weight is directly proportional to its mass, given a constant gravitational field. This relationship between mass and weight is a fundamental principle in physics, underlying everything from the falling of an apple to the orbiting of planets around the sun. Let's sum up the main differences between mass and weight. Firstly, mass and weight are measured in distinct units. Mass is measured in kilograms, a scalar quantity that only has magnitude. On the other hand, weight is measured in newtons, a vector quantity that encompasses both magnitude and direction. This difference in units is due to the underlying natures of these properties. Mass represents the amount of matter in an object, while weight is the gravitational force acting upon that object. Secondly, mass remains constant, regardless of where you are. Whether you're standing on Earth, floating on the moon, or drifting in the far reaches of space, your mass stays the same. It's a fundamental property intrinsic to you, no different than the color of your eyes or the type of humor you enjoy. It's an inherent part of you that doesn't change no matter where you go. Weight, however, is a different story. It's a bit of a social chameleon, changing based on where it finds itself. On Earth, you might weigh a certain amount, but if you were to go to the moon, your weight would be about 1/6 of what it is on Earth. This is due to the difference in gravitational acceleration between these two celestial bodies. To illustrate this, think of an astronaut. When they're on Earth, they experience a certain weight. But once they blast off into space, their weight decreases. However, their mass, the amount of matter they consist of, remains unchanged throughout the journey. So, when you're comparing mass and weight, keep in mind these key differences: their units of measurement, their inherent nature, and their response to different environments. Understanding these differences not only helps clarify these often confused terms, but also sheds light on the fundamental principles that govern our universe. Remember, mass remains constant, but weight can change depending on where you are in the universe. Why is understanding the difference between mass and weight so important, you may ask? Well, let's dive right into it. In the grand tapestry of physical sciences, the concepts of mass and weight are woven into its very fabric. They are fundamental building blocks that help us make sense of the universe and the laws that govern it. Take mass, for instance. It's an intrinsic property of matter that allows us to calculate an object's inertia. This is crucial in predicting how an object will behave when in motion. If you've ever wondered how engineers design vehicles to move smoothly, or why a bowling ball is harder to push than a tennis ball, then you've encountered the practical applications of mass and inertia. Mass also plays a significant role in understanding gravitational pull. The larger the mass of an object, the stronger it can pull other objects towards it. This is why planets, with their enormous mass, have enough gravitational pull to keep moons in orbit. Now let's consider weight. Unlike mass, weight is not constant. It's a measure of the gravitational force exerted on an object and changes based on where in the universe the object is. This is why astronauts feel weightless in space, even though their mass remains the same. Understanding weight is vital in assessing structural integrity. Engineers need to know the weight of materials to ensure that structures like bridges and buildings can withstand the gravitational forces acting on them. It also helps in determining the forces required to move objects. You see, it's not just about knowing how heavy something is. It's about understanding the forces acting upon it. So you see, mass and weight are not just scientific jargon. They're keys to unlocking a deeper understanding of the physical world around us. They enable us to design, create, and innovate. They help us grasp why and how things move, or why they stay still. So, the next time you hear about mass and weight, you'll know they are not interchangeable, and each has its unique role in the realm of science.
The credit for this video goes to Genesis of Chemistry, one of the best research consulting organization. For our services and offer, please visit our website. For more videos, please Like and subscribe to our channel, and join us on Facebook. Thanks.